Every time, you need to put install a plugin every time you want the software. That makes no sense. All right, sorry for the delay. We were locked out, but we're good now. Let's go ahead and jump in. We're going to start with E2 elimination. Hopefully by now, everybody has the handout, either electronically or physically. Let's start with, and before we do that, I can actually put this in the chat. If I can find it real quick. So if you're on your laptop, you should be able to see that in the chat. If you're on a device, you're not gonna be able to see it. Let's go to E2 reaction, and then we're gonna cut it, and we'll walk through it like we've done the other. And so we'll do E2 and E1, and then we'll do some examples. Very personal, right? All right, so we want to talk about E2 elimination. I'm going to take that bottom example, and that's what we're going to work through, because it's going to help us to answer a bunch of questions about the E2. The first thing that, the first characteristic I want to talk about is the actual substrate, right? You want that substrate either be tertiary or secondary. And that's on purpose, because if it's tertiary or secondary, first let me back up. For elimination, what is the outcome in the product? Always a double bond or a pi bond, right? So a secondary or tertiary carbon is going to give you a more substituted pi bond in the product. And I'll talk about what that means shortly. You get a more substituted pi bond in the product. That's why more substituted, more highly substituted substrates work better. All right, you need to do this in an aprotic solvent. That's on purpose, because you also need a strong base. Right, you need a strong base to do this reaction. Any E2 elimination is going to require the use of a base. And I sent a E2 video, I think, that talked about the different bases, and it's really a very nuanced discussion differentiating a base from a nucleophile. It's very nuanced. But for the sake of this discussion and for the sake of clarity, we're going to work from that list of bases that I gave you in the video, and I'll be happy to print that and upload it as well. So yeah, so you need a strong base. That's without saying, you have to have a strong base. And you want to do this in an aprotic solvent. And the last part about Zaitsel's rule, we're going to talk about that in the course of our discussion. Right? So here's the question. Based on what we've learned already about SN2, SN1. What does the 2 in E2 mean? What does that 2 mean in E2? That's not EC, by the way. My bad handwriting. What does that 2 mean in E2? What did it mean in SN2? Unity is 1, right? Bimolecular. So what does the 2 mean in E2? Bimolecular, right? It doesn't change. What does that mean for the rate law? Well, E2 is what does that mean for the rate law? K times what? You know the substrate is involved. Well, it would be nucleophile if we're doing substitution, but now we're doing elimination. So the nucleophile is going to be replaced by a base. But you're right. So it's K times the concentration of the substrate and the concentration of the base. All right, in this case, the base is the NH2 anion, or it would be KOH in the case of the second reaction. So that, again, that's us extrapolating information from something we already know. We know that SN2 is bimolecular, and it had a second order rate law, and it was a 2-term rate law. We can take that and say, well, if this is E2, then that 2 means the same thing, right? That's second order rate law, that's bimolecular. All right, let's look at the substrate itself. We're going to look at the bottom reaction because that one is going to give us a little bit more information about competition, and then we'll be able to talk about Zaitsel's rule as well. All right, so let's look at that bottom reaction. Where's my leaving group? This is my base. Right, that's written as A plus and OH minus. So where's my leaving group? How do I tell a leaving group? It's it's always the most electronegative atom or functional. So this is leaving group. Right. Everybody okay with that? Right. That's my leaving group. With elimination, there's another piece that I have to identify in that substrate. Once I find my leaving group, next thing is to identify what we call alpha protons or alpha hydrogens. Those are on the carbon next door to the leaving group. So these two right here those are alpha protons. And this also alpha proton. When you're solving elimination problems, find the leaving group first. This is a strategy. Find the leaving group first, and then find the alpha protons. Once you do that, you can figure out what the products are going to be, even if you don't know the mechanism. Right, because that leaving group has a carbon to the left and to the right. Both protons are equally, I don't want to say equally accessible, but both are reactive. All right, so what that means is that if I eliminate, and I'm going to show you the arrows too, so don't panic about that. But if I eliminate here, I'm gonna put a double bond right there. Right. If I eliminate from the other side, I'm gonna put a double bond right there. Y'all follow me? Anybody not see that? Are y'all following on Zoom? If you have a question, you gotta unmute and ask it, because I can't see the chat. I could if I sat down and talked, but I'm not. Everybody. All right, we good? So let's put the products in. Keep in mind, when I do an elimination, our leaving group gets lost, right? So there's no longer a part of our product. So this is going to be here. Let me draw it with the color. Right? And that double bond is going to be here, like that. This is going to be a competitive process because you got two alpha protons, two sets of alpha protons. So my other product is going to look like this. Double bond here. Questions about that? Look back at the start material, substrate, you can see we could predict what a double bond is going to be based on what a leaving group is. All right, and that's also, let me give you the side product. That's going to be plus AI. The iodine leaves, and potassium ends up with it. Potassium is a counter ion. So whatever is negative, potassium is going to find it and they get together. So plus AI plus water. Right? Any questions about that part? We're going to go through the arrows now. So don't freak out if you're not seeing it right away. Any questions about that part? Remember, anytime you do elimination, you're going to get a pi bond. You can eliminate and make triple bonds or double bonds. All right, so the more accurate way to say that is that you get a pi bond in the problem. All right, let's look at the arrows now. What side do you want to do first? Does it matter? All right, let's do the red side first. So here's my iodine. Right? I'm gonna put those red protons in. We're not worried about the O. All right. So the way this works is similar to an SN2. This is all concerted. So everything is happening all at once. So I'm going to bring in my OH. It's going to act as a base, right? So the first part is elimination, is proton transfer. So this is coming in like so. I'm going to attack that hydrogen right there. At the same time, that pair of electrons is going to come here, right? That's how I know where my double bond is going. And then at the same time, I'm losing my lead. It's all concerted. It all happens all at the same time. Right, it's concerted. So let's just think back to when we were looking at the SN2. If you constructed an energy diagram for this step, How many humps would it have? If everything is conserved. And there are no intermediates. One. It's gonna have one hump. Right? And depending on the bonds broken minus bonds formed, depending on the difference in that, you'll know if it's exothermic or endothermic. Can we calculate that? Anybody have, excuse me, access to that list, to that bond chart, energy chart? Like, is it handy for you? Like you can pull it out right now? Anybody? We can determine, I'm just throwing this in here because it's a good skill to have. We can determine if it's X or endothermic. We broke a CH bond, we broke a CI bond, we made an OH bond, and we made a CC pi bond. Is that right? Never mind. We'll come back to it. Did you find the chart? Okay, we'll come back to it. All right, so this is going to end up giving me, and I'm going to cheat and steal all.
Oh, you're talking about the chart we used last session, the bond show?
We'll come back to it. We're going to move. I have a double bond here. I still have this one hydrogen here that's left. And that's my first, that's how I get to my first product. And it's all conservative. So then I'll have water, HOH or H2O plus Ki, right? Because the K that was here, this is negative. The K that's here that's positive is going to end up with that I dot. That's what it leaves is going to be an anion. Any questions about anything? If you have a question on Zoom, you need to unmute and ask it. All right, let's look at the other side. Well, I'm just going to steal this and just repurpose it. Rather than, I normally do it on the same one, but I don't want to have anybody confused. Right, so we're going to look at this proton here. Right, the key is that nothing different is going to happen. Nothing different is going to happen. It's going to be the exact same mechanism, the exact same arrows, just in a different location. Right, so I'm going to show my base here. Negative. That's going to come in, pull off this proton. These electrons are coming here like that. Same thing, right? Lose the leaving group, well, force it out by making a pi bond, and then you do a proton transfer between the OH or the base, because it's not always going to be OH, and that alpha proton. That's going to give you this product. All right. So elimination, E2 elimination happens. Secondary, this is a secondary carbon, by the way. It can also happen at a tertiary carbon, which we see right here. So y'all can see here, but this is tertiary. Right, that's the preference. It can work on primary too, but the tertiary secondary work better because you get more substituted alkenes, right? Over here, let me just go through the alkene substitution paradigm, and then we'll come back and talk about that. right? So if you have an alkene like this, which is all hydrogens attached to it, this is considered unsubstituted. Right? It's all hydrogen, it's unsubstituted. If I add a carbon, one carbon, then it's mono. Right? Monosubstitute. Add two carbons. This is a pattern, right? Add two carbons. Di-substitute. Right? If I add three carbons, what do you think? Substitute, right? It's a pattern. And then four carbons, it will be tetra substitute. All right. The thing about alkenes is that the more substituted they are, the more stable they are. More substituted alkenes are more stable. So if we go back to the elimination, I'm going to talk about why they're more stable too. But if we go back to the elimination, which one of those alkenes is more substituted? Go back to the two products. So here's the double bond right here. This one for here. What we're looking for is what's attached to it. Right? So we have let's take the one on the bottom. We got a carbon here, and one here. So that's three carbons attached to that double bond. You can think about it that way, or you can think about the fact that you have one hydrogen attached. Right? Either way is logical. You got one hydrogen, then it's logical that there are three other things that occupy the other positions. But we got three carbons. So what's the substitution pattern? Let's try substitution. Right? What about the top one? We got a carbon right here and a carbon right here. Is that right? So the top molecule is going to be disubstitute. Anybody disagree with that or have a question? Right, so between those two, this one is more substituted and it's also more stable. Right, so according to what we call Zaitse's rule, the elimination, the major product, we go again with that. The major product is always going to be the more substituted alkene. Right? So if I had to attach percentages, let's just say this is, let's say 75 or 25. All right, so Zaxel's rule, write that down. You can say that the more substituted alkene is going to be favored. The more substituted alkene is favored in an elimination. Right, so when we say that the E2 elimination follows Zaxel's rule, what that means is that for this reaction, the major product will be the more substituted alkene. All right, any questions about that? All right, so Zaxel's rule says that for the E2 elimination or E1, which we'll talk about, maybe not today, but definitely Wednesday. For any elimination, the major product is going to be the more substituted product. Major product will be the more substituted product. They didn't give me, both of y'all wear glasses, so you wear glasses too? Okay, well, the writing is too small, say so, because I write like very small. Even when I'm using a dry erase marker, it's blue. So that's why I have to see and handwriting in elementary school and did make the honor roll. Handwriting. My mom did cuss the teacher out. But she didn't really cuss out. She just let her out a few words. Wasn't that bad. Thankfully, no camera phones, so nobody saw. Any questions? All right, let's talk about the stability part, and then we're going to come back, talk about the transition state and the energy diagram. We've already talked about the rate law. We know it's bimolecular, so we know that it's a two-term rate law. Let me ask this question before we do any examples. What if I triple the amount of substrate and double the amount of base? What's going to happen to the rate? I'm going to see if y'all were paying attention Friday. If I triple the amount of substrate and double the amount of base, what should happen to the rate? Should be a six-fold or six-time rate increase. Good. So the point is, whatever I do to either one of these components is going to change the rate. Not like SM1 or E1 is going to mirror SM1. This mirrors the SM2. So let's talk about real quick alkene stability, and then we're going to talk about the transition state. We'll probably stop. We'll probably be out of time. All right, I'm just going to go back with the tri-substituted alkene. Actually, I'll go with the tetra-substituted alkene. I'm going to put the carbon, I'm going to show the carbon in the alkene as well. All right, what is the hybridization state of the carbons in the alkene? I'll give you time to get that structure written down. What's the hybridization state of those carbons, the red carbons? sp2, good. They're both sp2, that's good. Now, one of the things that we talked about, or that we skimmed over, I got to go back and touch it because there's a link between hybridization state and electronegativity. Right? It was in one of the early videos. I don't know which one. It might have been in one of the highest videos. But there's a link between hybridization state and electronegativity. So we had SP3, SP2, come on, Russell. And SP, is that right? That's my hybridization state. And then the percent S character changes as you go through the hybridization states. As you go from SP3 to SP2 to SP, change. SP3 is 25% S. Is that right? If everything adds to 100, and you got 4 parts, so SP3 is going to be 25% S. SP2 is what? SP2, you got 3 pieces. 33 point something, 33333, but we're not gonna repeat decimal, we'll just say 33%. And then SP, is 50, right? It's 2 parts, and got to equal 100. All right, so it's 50% S for SP. What's happening here also is as that hybridization state changes, as the percent S character goes up, so does the electronegativity. So that electronegativity is increasing as you increase S character. So SP hybridized carbon is going to be more electronegative than SP3 hybridized carbon. If that makes sense. And there's a reason for that. The more S character you have, the more of the nucleus is exposed, right? So if the nucleus is more exposed, it's going to be more attracted to electrons from somewhere else. Right? More S character. Exposes the nucleus of carbon, and then of course the nucleus is positive of any atom is positive, so it's going to be attracted more to electrons. And make it more attractive. So that's how the electronegativity goes up, because the nucleus is a little bit more exposed. The carbon itself becomes a little bit tighter and harder. So with the nucleus more exposed, it's more attracted to electrons. Right? So if we take that information and go back to our alkene, those sp2 carbons are a little bit more electronegative than the sp3 carbons that they're attached to. Can you see that? So this is sp3. Is that right? So if there was a dipole between those, which way would it go? If sp2 is more electronegative than sp3, which way would the dipole go if you got those two atoms bonded together? See? You're saying what it would go this way? That's the, if this is more electronegative, the electrons should flow towards it, right? From the less electronegative atom. Is that right? Are y'all following that online? Huh? Annie here? More electronegative atoms pull electrons towards themselves. So if the sp2 carbon is more electronegative, the dipole is going that way. Is that right? The more carbon-carbon bonds you put around this, right? The more electrons are moving towards those sp2 carbons, that stabilizes those atoms. So they want the electron. So this is going this way like that, going this way like that. So those sp2 carbons are stabilized. When they're bound to electron-rich carbons, like that. So those sp2 carbons. That's why more substituted alkenes are more stable, because those carbon-carbon bonds are electron-rich, and they just shoot electron density towards those sp2 carbons. The term that we use for that, I think I gave you this term a while back. Talking about tertiary, primary, secondary, like that. Hyperconjugation. So that electron density is being shifted because of a dipole, and whatever that atom is that's partially positive or fully positive, it gets stabilized by that. All right, questions? We're good? Everybody okay? So that's why these things follow Lagrange's rule, because the more substituted your alkene is, the more stable it is, and stability is always the goal, right? You go from a less stable state to a more stable state. We got 3 minutes left. I don't want to go, and I could do the transition state in 2 minutes, but I'm not gonna do it, because then I'll be rushing and y'all glazed over anyway. We're gonna stop right here. All right, any questions from anybody online?